Hello everyone and welcome back. In this video we're going to cover page 66 and just the top of page 67 because all of this deals with the notion of absolute convergence. So you see here we're going to define absolute convergence in the following way. Let's suppose that you have a series, the sum of an, right? Then if you just put absolute value bars around each an, you get the following possibly different series, right? So it's the absolute value of A1 plus the absolute value of A2 plus the absolute value of A3 plus etc. etc. If you have an old version of the notes, I forgot to put the absolute values there, so I fixed that and re-uploaded the notes. So please check that out on the course Moodle page. Anyway, we call a series absolutely convergent if this new series, where you just take the absolute value of every single term and add those together, if that series converges, right? The only way that these two series are the same is if the ANs were positive already, right? Because then the absolute value doesn't do anything. But most series that you run into, they're not necessarily all with positive terms. Like we saw above, you may have alternating series, that kind of thing. And now a series is called conditionally convergent if this series converges, just the sum of AN, but when you throw absolute value bars around the AN, it does not converge, right? So we'll see an example of that in just a minute. But first, let's start with this example here. So let's find out if it's absolutely convergent, right? Now, when you're dealing with absolute convergence, it's best to just swing for the fences. So what we're going to do is we're just going to ask right up front, is this absolutely convergent? Okay. Well, here's what you do. You look at the sum n equals 1 to infinity of the absolute value of the summand. And remember what we said all the way back in section 8.1, absolute value bars kill the alternating part. And so this is really just the sum n equals 1 to infinity of 1 over n squared, right? And so when I throw absolute value bars around the summand, I get a convergent series. So this series converges, let's see, well, how do we know this converges? Well, it's a p series with p equal to 2, right? So therefore, the original series, we say converges absolutely, or we also will say is, so I guess I'll say or, is absolutely convergent. And now what this means is that not only does this series converges, but it's even a stronger notion than that. It converges even when I throw absolute value bars there. So absolute convergence implies convergence. You see that's a theorem right here. Absolute convergence implies convergence. But the other way around is not true. A series can converge, but not absolutely. And we'll get to that in just a second. But what I want you to think about is how would you show that this series converges without using the fact that it's absolutely convergent? Maybe use AST, right? It's not necessary. We already know that it converges absolutely, but it is something to keep in mind, right? Okay, so let's come over here to this second example. And again, we're going to swing for the fences. We're asking, does this series converge absolutely? So is this absolutely convergent? Well, we take the sum n equals 1 to infinity of the absolute value of the summand. This is the sum of 1 over n. Oh, but we know this diverges. Why? It's the harmonic series, right? And remember, we know the harmonic series diverges, but the fact that the sum of the absolute values diverge doesn't tell us anything about this. All we know is that this series is not absolutely convergent, right? It possibly still could converge or diverge. So the next thing you would try is you would try to show that just the series as you're looking at it So instead of swinging for the fences, since we know it's not absolutely convergent, can we show it's just normal convergent? Well, if you look at this, if you remember from last video, or I guess 2 videos ago, the beginning of section 8.4, this is the alternating harmonic series. And we know that this converges by the alternating series test, right? So you would identify Bn, which is 1 over n, that's decreasing and goes to 0. So this alternating series, the alternating harmonic series, converges by the alternating series test. And so here we go. This is our definition just above here. The series converges, but not absolutely. And so we say, therefore, that the sum n equals 1 to infinity minus 1 to the n minus 1 all over n is conditionally convergent. Or converges conditionally, if you want to say it that way. Either way is fine. All right. So let's come to this final example on page 66 here. We have this series here. Well, again, does it converge absolutely? If you're being asked that, then go ahead and try to swing for the fences. So let's see here. We get sum n equals 1 to infinity, absolute value sine 4n over 4 to the n. Notice these are different here. This is a sine of 4n, whereas this is 4 to the n. Well, this is the sum n equals 1 to infinity. Property of absolute value says I can do the absolute value of the top divided by the absolute value of the bottom. But the absolute value of 4 to the n, because, I mean, that's just 4 to the n. 4 to the n is already positive, so absolute values do nothing, right? Now, sine does need the absolute value because think of sine values. As you go around the circle, you get positive and negative sine values. Okay, well, here's a key observation. We don't really know anything about this series, but I do know that no matter what sine outputs, that number that sine outputs will always be between minus 1 and 1, right? The output of sine is always between minus 1 and 1. And so the absolute value of that is less than or equal to 1. So you can take that to the bank with you. The absolute value of sine is always less than or equal to 1. And so now I'm using a direct comparison. This series here way on the right over here, I know this converges. Can you think of why? It's geometric with r equal to 1/4. And so the sum of the absolute values here is less than a convergent series, and so this series converges, and therefore you would say that, I'm sorry, this converges by comparison, or direct comparison if you like. And therefore, because this series with the absolute value bars converges, we conclude that the series without the absolute value bars is absolutely convergent. Okay. So if you swing for the fences and hit a home run, then you just conclude absolutely convergent and everything is fine, right? You only have to worry about conditionally convergent if you conclude that it's not absolutely convergent, as we saw in the last example. All right, so let's come over to this one here. Well, we're being asked, is this absolutely convergent? So again, we swing for the fences. So we take the sum n equals 2 to infinity, absolute value minus 1 to the n over n ln of n. Well, the absolute value kills the alternating part. Since n is greater than or equal to 2, n times ln of n is always positive, so this is just 1 over n ln n, and the sum of that, right? Let's see. Any idea about this series? Well, this may look familiar. You actually showed this diverges by integral test. I think that was on homework 8. All right, so I'll say C homework 8. So this series is not absolutely convergent. Is it conditionally convergent? So I guess I'll say absolutely convergent? No, right? But is it conditionally? Well, how would you show it? Notice it's alternating, right? So first of all, we can apply the alternating series test, and hopefully that'll work for us. We identify Bn, the non-alternating part, which is 1 over n ln of n. Is it decreasing? Well, as n gets bigger, both natural log and n also get bigger, so the denominator is getting bigger with each increasing n value. So Bn is decreasing. That's good. And furthermore, is the limit of 1 over n times ln of n, is that equal to 0? Well, yeah, as n gets large, that's an infinity there. As n gets large, both of these are getting arbitrarily large, so 1 over that is a very small number, i.e. 0. So what we see is that this series, n equals 2 to infinity minus 1 to the n over n ln of n, converges by AST, alternating series test, but it's not absolutely convergent, and so we therefore conclude conditional convergence. Okay, so that's all we have for right now for absolute convergence. We'll get into the ratio and root tests starting in the next video.